Organic chemistry, just hearing those words can be a little intimidating, right? But what if I told you it's not really about memorizing a phone book of reactions? What if it's actually just a game of logic? Let's dive in and figure out the rules together.
You know, the biggest myth about organic chemistry is that it's this impossible mountain of facts you have to cram into your brain. It feels like trying to learn a new language, but one with an infinite dictionary. It's no wonder it has such a scary reputation.
But here's the thing, that's not the real story. Hiding underneath all that complexity is a surprisingly simple and honestly, an elegant set of rules. Today, we're going to pull back the curtain and show you that system. We're going to turn this subject from something you fear into something you can actually master.
All right, first things first. We have to define our terms. The word organic is thrown around all the time, but in the world of chemistry, it means something very, very specific. So let's start there with the official definition.
Okay, so here it is. An organic compound is a hydrocarbon. That's just a fancy word for something made of hydrogen and carbon. And its derivatives. Now, hydrocarbon, that's pretty simple. But that second part, derivatives, that's where all the interesting stuff happens.
So your brain probably just went, hold on, what exactly is a derivative? And that's the perfect question, because it's not just anything that can be made from a hydrocarbon. A compound has to pass a very clear two-part test to get that title. And here are the two big rules. 1. It absolutely has to be produced from a hydrocarbon. And 2, this is the real kicker. It has to have chemical properties that are similar to the hydrocarbon it came from. You gotta have both. One with the other doesn't count. Let's make this real. Take methane, CH4. If you react it with chlorine, you get chloromethane. Its properties are pretty similar to methane's, so check, it passes the test. It's a real derivative. But if you burn that same methane, you get carbon dioxide, CO2. Now, even though it came from methane, are its properties similar? Not at all. Methane is a fuel. Carbon dioxide is what you get when the fuel's all gone. It's a totally different beast. So it fails the test. It is not considered an organic derivative. You know, this clear definition we have now, it wasn't always so obvious. For a long, long time, scientists thought organic compounds were special, like they were cooked up with some kind of magical life force. And it took one single, accidental discovery to change everything.
Let's hop into the time machine and go back to the early 1800s. In 1815, a chemist named Berzelius comes up with this huge idea. But just 13 years later, which is pretty fast in the world of science, another chemist, Friedrich Wöhler, accidentally blows that theory out of the water and sets chemistry on a completely new path.
So, Berzelius's vital force theory was pretty straightforward. He looked around and saw that all the organic compounds he knew about came from living things, plants and animals. So he figured they must have some mysterious vital force from life itself. And because of that, humans could never, ever make them in a lab. And then Wöhler comes along. He wasn't even trying to prove anything big. He was just in his lab heating up a totally non-living inorganic compound called ammonium cyanate. And by accident, he created urea, a compound that is 100% organic. It was the first time ever an organic molecule was made from inorganic stuff in a lab. And just like that, poof, the idea of a vital force vanished, and modern organic chemistry was born.
So Wöhler's discovery proved the magic wasn't a life force. It was something about the atoms themselves. And that brings us to the real hero of our story, the carbon atom. It's the superstar, the backbone of every single organic molecule, and understanding its unique personality is the key to the whole field. We all learn in school that carbon can form 4 bonds, and that's why it's so great at building all the amazing and complex molecules of life. But that brings up a really interesting question. Are all 4 of those bonds exactly the same? Logically, they probably shouldn't be. And here's why. See, in its natural state, carbon has electrons in different orbitals with different energy levels. If it just used those to make bonds, you'd get some stronger bonds and some weaker bonds. It'd be like trying to build a chair with legs of different lengths. The whole thing would be wobbly and unstable. But we know from reality that molecules like methane are incredibly stable. So how does nature fix this problem? Well, carbon has this amazing trick up its sleeve called hybridization. It basically takes its different atomic orbitals, throws them into a blender, and creates a brand new set of identical hybrid orbitals that all have the exact same energy.
Okay, this is my favorite way to explain it. Imagine you have 3 different kinds of mangoes. They're all a bit different, right? If you just give them to 3 people, they might argue about who got the best one. But if you put them all in a blender, that's our hybridization, And then pour out 3 glasses of juice. What do you get? 3 perfectly identical glasses of juice. Every single one is the same. That's exactly what carbon does.
Understanding the why behind hybridization is great, but let's get practical. Let's talk about the how. Turns out there's a really simple tool, a little shortcut you can use to figure out a carbon atom's hybridization just by looking at the bonds it's making.
This little table right here, this is going to be your best friend. It's super simple. If you see a carbon atom and it has only single bonds, its hybridization is sp3. If you see it has one double bond, it's sp2. And if it has one triple bond, it's sp. It's a fantastic shortcut that works like a charm almost every time.
So for example, in a simple molecule, a carbon with all single bonds is sp3, and one right next to it with a double bond is sp2. See? Piece of cake. This shortcut makes things feel way easier.
But every shortcut has its limits. What happens when you see something a little tricky, like this molecule where the carbon in the middle has double bonds on both sides? Does our rule still work? Does it have a double bond, so it's sp squared?
This is where we need to look past the shortcut and remember the fundamental principle. Hybridization is really about creating orbitals for something called sigma bonds. Those are the direct head-on connections between atoms. That central carbon only forms 2 of those sigma bonds, and to make 2 sigma bonds, it only needs 2 hybrid orbitals. So, its hybridization has to be sp.
And this right here is the big takeaway. The shortcuts are awesome, they'll get you through most problems, but understanding the underlying principle, that hybridization is all about the number of sigma bonds, that's what gives you real power. That's the logic that will never, ever fail you.
So when you really get the rules for what makes something organic, when you know the history and you understand the deep logic of how carbon behaves, the whole subject just transforms. It stops being about memorization and it starts being about solving puzzles.
You now have the fundamental key that unlocks organic chemistry. It's not some big, scary monster. It's a game with a clear set of rules. And now that you know the rules, you're ready to play. So, the only question left is, what puzzles are you going to solve first?